In this video, we're going to talk about how to count outcomes using a tree diagram, which is going to lead us to the fundamental counting principle. In many cases with probability, there is more than one action or choice, and determining the sample space and the number of possible outcomes can be tricky. A tree diagram organizes and shows all the possible outcomes from multiple events. Tree diagrams are particularly useful in probability since they record all the possible outcomes in a clear and uncomplicated manner. Let's look at an example. Felix is going to buy a pair of shorts, a shirt, and a pair of shoes at the store. And he wants to choose one item from each category. He can choose khaki or green shorts, white, yellow, or orange shirts, or sandals or sneakers, which are shoes. What's the probability of Felix choosing a pair of green shorts, a yellow shirt, and sandals? We can create a tree diagram to help us figure this out. So to figure out the number of So it's still the concept of the number of favorable outcomes, which in this case would be choosing a green short, yellow shirt, and sandal, over the total number of possibilities. But how many different outfits could he make out of these shorts, these shirts, and these shoes? So a tree diagram can help us to see this. Now this looks kind of complicated, but just bear with me. So this is event 1, choosing from khaki or green shorts. And then off of khaki, you're going to put all the possibilities for shirt, which is white, yellow, orange. And off of the green shorts, you're going to put all the possibilities for shirts, which is white, yellow, orange. So we could have khaki shorts and white shirt, khaki shorts and yellow shirt, khaki shorts and orange shirt, and so on. And then off of each shirt, so this is a second event, choosing the shirt, and this is a third event, choosing the shoes. So off of each possibility of shirt, you're going to put both possibilities of shoes, sandals and sneakers, sandals, sneakers, sandals, sneakers, blah, 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 blah. And then this leads to all of my different outcomes. I could have khaki, white, and sandals. I could have khaki, white, and sneakers. I could have khaki, yellow sandals. I could have khaki, yellow sneakers. If you follow each branch of the tree, you get a different outcome. So you can see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 outcomes in my sample space. And one of them is the favorable outcome of green shorts, yellow shirt, and sandals. So the probability of picking green shorts, yellow shirt, and sandals is 1 out of 12. Let's look at the creation of this with flipping a coin. So Claire is going to flip a coin 3 times. So we're going to have event 1 is flipping a coin, and then event 2 is flipping a coin, and then event 3 is flipping a coin. So on the last one, our events were choosing shirts, shorts, and shoes. Here it's the same event, it's flipping a coin 3 times. So we have 3 separate events of flipping the coins. And the probability we want to find is if it's going to be heads, tails, tails. So that's the outcome that we want. So event 1 is going to be heads or tails, right? Those are our possible outcomes from event 1. From event 2, our possible outcomes are still heads or tails. And we're going to put that off of each event from number 1. So that's the key. Is whatever the outcome is, the possible outcomes for event 2, you're going to repeat those same outcomes for each event 1. You see? And then same thing for event 3. We're going to have another set of heads and tails for each event outcome from event 2. And I didn't do a great job of spacing this out, but this goes with this heads and this goes with this tails. So we have a possibility of heads, 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 tails, heads, tails, heads. And you have to follow each branch, make sure you're following each branch, heads, tails, tails, to get all the different possible outcomes. And of course, this can be a little bit tedious depending on how many different choices you have. But it also is really effective at showing these are all the different outcomes of my sample space from flipping a coin 3 times. And we want the outcome that is heads, tails, tails. And there's only one outcome. So the probability is 1 out of 1, 2, 3, 4, 5, 6, 7, 8 outcomes in my sample space. So the probability is 1/8. Now there is a bit shorter way to come up with that. You can see I have two possibilities here, and then for each one of those, I have two possibilities for a total of 4 possibilities. And for each one of those, I have 2 choices for a total of 8 outcomes. And that leads us to the fundamental counting principle. The fundamental counting principle is if one activity can occur in m ways, let's say heads and tails, that's 2 ways, and another activity can occur in n ways, let's say that's heads and tails too, then both activities can occur in m times n number of ways. So you just multiply the different options from each event together, and that will give you the total number of outcomes for the event, the multiple events occurring. The counting principle applies when we are selecting one item from each group and trying to determine the number of outcomes. So we have separate groups or separate events. We're flipping a coin, and then we're flipping a coin, and then we're flipping another coin. And we're doing separate events, or we're selecting from separate groups. That's the fundamental counting principle. Here's an example. If you're given a choice of 3 different sandwiches and 2 different drinks, so 2 different groups, 2 different events, choosing a sandwich, choosing a drink, then we can use the fundamental counting principle, which is just 3 times 2. There are 6 different combinations that I can choose. We could draw a tree diagram and do our 3 branches for our sandwich and then 2 drinks off of each one. And you can see 1, 2, 3, 4, 5, 6 different possibilities. A couple of more quick examples. Ron is going out to pasta dinner. There are 3 types of noodles to choose from and 6 choices of vegetable. How many different pasta dinners? Again, 2 different categories that we're choosing from. So we just take it 3 times 6 is 18 different pasta dinners. Another example, while preparing a recording for application in music school, Bernie must follow very specific requirements. The recording must have 1 classical song and 1 jazz song. Bernie is proficient at 3 classical songs and 2 jazz songs. Assuming the order of the songs doesn't matter, how many different recordings can he make? So there's 3 classical, 2 jazz. He could make a possibility of 6 different recordings. Again, we are selecting one thing from 2 different groups. We just multiply how many options we have from each group, how many outcomes can occur from each group. That's going to be the total number of outcomes.